Hello everyone, thank you for joining me today. I'm going to talk about text generation with large language models and how we can optimize the inference hyperparameters for both utility and cost. My name is Susan Liu from Stevens Institute of Technology. This work is done by Wang, myself, and Ahmed Awadallah. It's a first study of inference hyperparameter optimization for LLM. Here is the outline. First, I'll briefly talk about the background on text generation with LLMs and why it's important to consider both utility and cost when using them. Next, I will introduce our optimization framework, EcoOptiGen, which aims to find the optimal inference hyperparameters for a given task and budget. It leverages economical hyperparameter optimization and cost-based pruning. Then I'll show you some experiments we did with GPT 3.5 and GPT-4 models in the Helm benchmark using 4 different text generation tasks. Finally, I'll discuss some future work directions. No one here would doubt the usefulness of text generation with LLM. What's interesting about the LLM is that even though they don't always generate perfect answers, they can be used to build very powerful user experiences already. The other side of the story is that the monetary cost of using LLM is a concern for various reasons, such as profitability. Therefore, we need to find a balance between utility and cost. For example, there are smaller and cheaper models like GPT 3.5 Turbo, but they are less reliable for difficult tasks such as code generation. Larger language models are more capable but also more expensive. From the perspective of an application builder using LLMs, the goal is to maximize the utility of the generated text under an inference budget constraint. This can be achieved by optimizing the hyperparameter of the inference. Little is known about how to optimize the different hyperparameters collectively and systematically, especially for generative tasks. The OpenAI API has 10 tunable hyperparameters, same for the one offered by Azure Cognitive Service. There are some complex interactions among subsets of the hyperparameters. For example, the temperature and top P are not recommended to be altered from their default values together because they both control the randomness of the generated text, and changing both at the same time can result in conflicting effects. Both n and max tokens will affect the total number of tokens generated, which in turn affect the cost of the request. These interactions and trade-offs make it difficult to manually determine the optimal hyperparameter settings for a given text generation task. To help developers find the optimal setting, we propose to develop an automated optimizer. Users could specify a range of values for each hyperparameter, and our optimizer finds the best combination. Our optimizer takes the following input: tuning data, utility function, budget constraints, and search space. It outputs an optimal config with highest utility under the budget constraint. The previous slide explains the default search space when users don't provide it. Let me explain the other input. This is our architecture. It includes a hyperparameter searcher and a configuration evaluator with pruning. The hyperparameter searcher we use is blend search. Now let's discuss the configuration evaluator. A simple evaluator takes a configuration X as the input and outputs the metric to optimize. It loops over the data examples in D. For each example in D, a request is made to the LLM service using the configuration and the input field in the data example. The responses from the LLM service are then used to compute the utility U and measure the cost consumption C. When the loop is over, the average cost CXD is compared with the user-provided bounds B.I. If CXD is smaller or equal to B.I, the average utility UXD for all the data in D is returned. Otherwise, the zero value is returned to indicate that the configuration is invalid. If a configuration is invalid, it is beneficial to terminate the trial early to save unnecessary cost. A full evaluation of a configuration X needs to send D LLM requests, each asking for x.n responses, where x.n is the setting of the hyperparameter in n in configuration X. Our goal is to spend a much smaller cost in invalid trials. For a given configuration X, before the expensive evaluation starts, we first check whether we could prune the configuration directly. This check assumes a property of the LLM. What it implies is that we know a particular configuration is valid. The configurations with smaller number of responses and smaller max tokens are valid too. If a configuration is invalid, the configurations with larger number of responses and larger max tokens are invalid too. That gives us opportunities to assess the validity of configuration without making expensive requests to the LLM. After we evaluate a few configurations, there are 3 cases for a new configuration to be evaluated: expected to be valid, expected to be invalid, or we don't know. In the first case, we evaluate the configuration as it is. In the second case, we prune this trial without evaluation. In the third case, we start evaluating the trial from a small number of responses which we expect to be valid. Then we gradually double the number of responses n until it reaches the specified number of responses of this configuration, or until it is pruned. This example illustrates how the pruning works, how the valid and invalid regions change as more evaluations are made, and how early stopping saves evaluation costs. Here is a case study for math, a benchmark for evaluating LLMs on advanced mathematical problem solving. Math consists of 12,000 math competition problems from AMC 10, AMC 12, and IME. Each problem is accompanied by a step-by-step solution. The first figure shows the average accuracy and average inference cost of each configuration on the level 2 algebra test set. Surprisingly, the tuned GPT 3.5 turbo model is selected as a better model, and it vastly outperforms untuned GPT-4 in accuracy, 92% versus 70%, with equal or 2.5 times higher inference cost. The same observation can be obtained on the level 3 algebra test set. For easy problems, the tuned GPT 3.5 turbo model vastly outperforms untuned GPT-4 in accuracy. For example, 90% versus 70% in cost efficiency. For hard problems, the tuned GPT-4 is much more accurate. For example, 35% versus 20%, and less expensive than untuned GPT-4. We can see that our tuning method has found different optimal model and inference parameters for each subset of a particular level, which shows that these parameters matter in cost-sensitive LLM applications and need to be carefully tuned or adapted. Just by tuning the inference parameters like model, number of responses, temperature, etc. without changing any model weights or prompt, you can improve the state-of-the-art GPT-4 by 20% in high school math competition problems. And you get that performance improvement while paying 15 to 25% less. It will also be good to further automate the tuning and deepen the understanding of the utility cost trade-off. For example, the current solution takes the user-specified choices of prompts as the input search space. Automatically searching for optimal numbers of choices of demonstration examples can potentially result in more effective ways of using the inference budget. It will be interesting to explore more tasks such as prompt optimization and instance-level optimization. Our solution is released in a package AutoGen in the open source project Flamel. AutoGen is AutoML for GPTX applications. We're excited to hear your feedback and work with the community to advance this field.